Hi everyone, in this video we're going to be learning about systems of linear equations. And so a linear equation with variables x sub 1, x sub 2, and so on all the way to x sub n is an equation that has this form where a sub 1, a sub 2, and so on are coefficients and they're real or complex numbers, and so is b. And so notice what you have a linear combination of your variables. And so one of the things with linear equations to remember is that the variables are always to the first power. And now a system of linear equations, you can also call this a linear system, is just a collection of one or more linear equations that involve the same variables. So when you're working with a linear system, you're ultimately looking for a solution. And so a solution to the system is a list of numbers that make each of the statements true when you sub them into your variables. So basically, a solution satisfies each equation in your system. So if x is your variable, x1, you're solving for x1. You're saying x1 equals something, x2 equals something, and so on. Whatever makes each of the equations in your system true. We call that a solution. And then the set of all possible solutions is called the solution set of the linear system. And anytime two linear systems are equivalent, it's because they have the same solution set. So there's three possible outcomes when you're trying to solve a system of linear equations. So the three things that you're going to come across, a lot of the times it's going to be one solution, but three outcomes are that there's no solution, there's exactly one solution, or there's infinitely many solutions. So keep these in mind, because no matter which linear system you're trying to solve, you'll get one of these three outcomes. And like I said, a lot of the time it's going to be number 2 here, but not always. And so just so you're aware how you'll know what you have, an exact solution is when you're able to solve for your variables and get numbers. Infinitely many solutions, you're going to get something that's maybe like a true statement, but one of your variables, at least one of them, will be considered free. You won't be able to necessarily solve for it. You'll get something like x1 equals itself. Or no solution would be if you get something that's false, like a false statement, like 0 equals 3. So those are the possible outcomes anytime you're trying to solve a system of linear equations. Now, if a system has solutions, either one or infinitely many, we can call that system consistent. And anytime a system doesn't have a solution, we call it inconsistent. So inconsistent, no solution. Consistent, solutions, one or more. All right, now we're ready for our matrix notation. So for a linear system, what we actually do, because sometimes we're working with some pretty large system of equations, is we write it in matrix form. And so here's an example of a system of linear equations. Notice that this system has 3 equations in it, 1, 2, 3. And you have your same variables. They don't all have to be there. Like notice equation 2 doesn't have an x1, but you still have the same variables going on in each of these equations. And so what we do is we kind of write this more condensed in matrix form. And so here is what's called the coefficient matrix for this system. And so notice where you get these numbers from in this system or in this matrix. Look at your first equation. The coefficients are what's in row 1. So there's 1x1, that's why there's a 1 here, minus 2x2, that's why there's a minus 2 here, plus 1x3, and that's why there's a 1 here. Your second equation, because there's no x1, that's why there's a 0 here in the x1 column. And so the x2 column is your coefficients from x2. Notice what you have, negative 2, 2, and 5. And then your third column is your x3 coefficients, 1, negative 8, 9. And so we also have what's called a augmented matrix, where you put the answers in here as well. But this one is just called a coefficient matrix. So the augmented matrix involves what equals our equations. So notice we have a new column. Our fourth column here was what each of our equations equaled. So most of the time you're going to be working with augmented matrices whenever you're trying to solve a system of linear equations. And sometimes people draw like a dashed line. So if it helps you when you're doing work, feel free to do something like this. I've seen a lot of people do this, to make a dashed line so you know that that's your answer column. Okay, so then now that we see what matrix notation looks like, we are interested in the size of the matrix often. And the size of the matrix, the way we would say it is it's an n by n matrix. M represents the rows and n represents the columns. So rows is always first. So if you have 3 rows in your matrix like we had, and then for our augmented one we had 4 columns, we would call that a 3 by 4 matrix. Now, the basic strategy for solving linear systems is to replace one system with an equivalent system that's easier to solve. And so we'll go through this process. There's steps for this, but basically you do steps to rewrite your matrix over and over again until you get to our ultimate goal, which I'll explain in just a minute. And so basically when you have a system of linear equations and you put it in matrix form, we try to get to where we have ones in the diagonal and zeros everywhere else. Because if we could do that, then we have our answers for our variables. And I'll explain that when we get there. So then our solution for this example is we're going to eliminate variables without a matrix. We're not going to use the matrix notation at first, but then we will also use the matrix notation and compare this. Okay. So here is our system in just its regular equation form. Here is the same system as an augmented matrix. So think back to what you learned in college algebra about systems of equations. You can do your elimination method to solve for your variables. If you notice here, I have equation 3. Okay. If I add 4 times equation 1, so look at equation 1, times each term by 4, you will get this equation right here. Okay. If I add these two, so let me put that. So if I add these 2 equations, notice what I'm going to do. This is going to be eliminating my x1 variable. I have a total of negative 3x2s, and then I have a total of 13x3s, and that's a new equation. So we had 3 equations to start with. We can call this one equation 4 now. So what I called equation 4 can actually replace one of our original 3 equations. And so notice what we have. Our third row in our matrix form of our system is replaced with what we got from our new equation. Okay, and so this is the whole idea that we just talked about of replacing our system of equations with an equivalent one. So technically this matrix is equivalent to the one that we began with, but it looks different. So let's keep going. Now we're going to multiply our second equation, which is this one here, by 1/2. You can think of that as like dividing by 2. And then we want to get 1 for the coefficient on x2. That's the whole point. So what we're actually doing here, and I mentioned this, is we're trying to get 1s in the diagonal right here. That is your ultimate goal when solving matrices. Because if you get 1s in the diagonal, and then zeros everywhere else except for the answer column. So the answer column can stay just any numbers. If you get 1s in the diagonal and zeros everywhere else, then you have your answers. You have that 1 x1 equals whatever numbers over here in your answer column. You have that 1 x2, which will be right here, equals whatever's in the answer column. And then over here, this will be 1 x3, because this would be a 1, and above it would be zeros, equals whatever's in the answer column. So your ultimate goal is to get 1s in the diagonal and zeros everywhere else. Now real quick, there is a preliminary goal. You can actually just get zeros in these bottom left area. We call that triangular form. If you focus on getting zeros here and 1s in the diagonal, then you can still finish this system by solving it using substitution. Okay, so notice what we did. We changed equation 2 by multiplying by 1/2, or think of that as dividing by 2, but technically we multiply. And so that replaced our original row 2. So then we keep going. Look at what we're trying to actually get to now. So remember what I told you, you want to get 1s in the diagonal. So we're almost there. We have a 1 here, we have a 1 here, and so this needs to become a 1. And so this is a little bit of a problem-solving process. You have to look at your equations and think, how do I get that? How do I get what I'm looking for? I'm looking to make this coefficient on x3 become a 1. And so we're going to work with that equation. So this is equation 3 right now. We work with that equation and we say, what can I do to this equation, or maybe another one in my system, to be able to get a 1x3? And in this case, we're going to use equation 2. We're going to borrow equation 2. So notice this is equation 2 right here. But it's equation 2 multiplied by 3. So if we times equation 2 by 3, so right here, if we times this by 3, we get 3x2, and this becomes 3 times 4, that's where the negative 12 came from, and then equals 12. And then if we add those, we get x2 eliminated, a total of 1, x3 equals 3. And so that's going to replace our row 3. So an equivalent system where we used our equations to change what this looks like, but technically is still equivalent. So the next thing we're going to write is that our third equation, or third row, is just 1x3 equals 3. Okay, so here's what we have. Okay, so this is your preliminary goal, and you can stop here because you can finish in this form. It's called triangular form. You can finish solving for your variables in this form where you have zeros down here and 1s in the diagonal. But if you kept going, you would want to get zeros here above your diagonals as well. And then that's the ultimate goal, because then you're done. You don't have to do anything extra. So the equivalent system of equations is over here on the left. This is what it looks like with your variables and your equal sign. This is what it looks like on the right in matrix form. So these are the same thing, they just look different. Okay, and so we have on the right side the same thing as equation 1 is row 1. Okay, equation 2 is row 2, and then equation 3 is row 3. And then from here, what you could do to finish solving is substitute. We know that x3 is 3, so you can plug that into equation 2 or row 2 and solve for x2. And then once you know x3 and x2, you can plug both of those into equation 1 and solve for x1. But we're going to go ahead and keep going and get this in our completely reduced form of 1s in the diagonal and 0s everywhere else. So the next thing we're going to do is we're going to make the rest of the coefficients in the x3 column, we're going to make those 0. Okay, so if I multiply equation 3 by 4, so this was equation 3, and just a quick note, it helps to label things. So as you're working, one of the things that happens a lot of times is people get pretty disorganized with this if you don't stay purposefully organized. So if you need to, make yourself notes. That way you can keep track of what you're doing. And so this was our equation 3. And so things that I like to do is say what I did. So I would say like 4 times row 3. And another way to write that, if you're doing it in matrix form, is to say 4 times row 3, because equation 3 is the same as row 3. So you can write it like that. That way you keep track of what you're working with. Okay, and then this was equation 2. And so what we did here is we said 4 times row 3 plus row 2. So remember, you're just doing your elimination process. And if you do that, 4 times row 3 plus row 2, you get x2 equals 16. And so that right here, this equation, replaces row 2. So that's right here. Okay. And then to get the 0 in row 1, in the x3 column, we can say negative 1 times row 3. And then we can add that to row 1. So let me change that real quick. So add that to, this was row 1. Okay, so then we had negative x3 plus x3, so those are eliminated. That's where this 0 comes from down here. And then we have 1x1 minus 2x2 equals negative 3, and that's what replaced our row 1. Okay, and so we want to do one more thing to finish this, is we want to turn this negative 2 into a 0, because remember, we want zeros everywhere except the diagonal in the answer column. So I'm focusing on this very last spot. I want that to be a 0. So let's think about how we can do that. The only actual equation we can use is equation 2, or row 2. So what I'm going to do, if I want my x2 to become a 0, I can say 2 times row 2, and then I'll add that to row 1. Okay, so I'll say row 1 plus 2 times row 2, because if I say 2 times row 2, this is going to become a 2x2, and this is going to become 32. And then if I add, look what happens. I'm going to get a x1, which is the 1 right here, and then I'm going to get 0x2, so that's going to become a 0. And then 32 minus 3 is going to be 29, so let's see. And that's what we have over here. So we actually call this reduced echelon form, but this is the goal. So when you guys are solving your systems of linear equations in matrix form, you want 1s in the diagonal and 0s elsewhere. Because if you have that, it says, if you translate it back to equations, it says you have 1x1 equals this number, 29. This row says you have 1x2 equals the number here, 16. And then the third row says that I have 1x3 equal to 3. So that's why you want to get 1s in the diagonal and 0s elsewhere, because then you can get your answers just by looking. Okay, so what we found was one solution. So this system of linear equations had exactly one solution, and because it was 3 variables, we can write the answer as an ordered triple. So we had x1 was 29, x2 was 16, and x3 was 3. Now, anytime you're not sure if you did this right, you can always verify by substituting your values of your variables back into your original equations. So if you go back, this was equation 1, this was equation 2, and this was equation 3. And you just plug in your variables everywhere for x1, x2, and x3. And you should get what it's supposed to equal, and we do. So in this case, equation 1 was supposed to equal 0, and it does. Equation 2 was supposed to equal 8, and equation 3 was supposed to equal negative 9. Okay, so now let's talk about our elementary row operations. Pretty much it's everything we just did, but I want you to be aware of what you can do with the matrix. So there's only a few things. What you're allowed to do to write an equivalent matrix to your original is you are allowed to replace, interchange, and scale. And so replacement is when you replace one row by the sum of itself and a multiple of another row. We did this quite a few times. We multiplied a row by a number, and then we added it to another row, and then we used that resulting equation to replace one of our original rows. So that's replacement. You can also interchange 2 rows. So let's say one of your rows had like 1, 0, 0 in it already, but it was not, like the 1 wasn't in the right spot according to your diagonal. Then you can interchange it with another row to put it in the right spot. If, like, let's say the 1 was in the first position, then we would want that to be row 1, so we can interchange it there. And then the third thing we're allowed to do is scale. So that's just multiplying. So you can multiply a row by a number other than 0. So we did that a lot too. You can multiply by 2, you can multiply by 1/2, You can multiply by any number other than 0. So those are the 3 things you're allowed to do to your rows. And I recommend that you keep track. So just write a little note for what you did in each step, because a lot of times you'll have like a paper full of work where you wrote equivalent matrices over and over again. And it really helps to write what you did for your steps, especially if at the end your answers don't check out. You can kind of backtrack and see where you might have made a mistake. And then 2 matrices are called row equivalent if there is a sequence of elementary row operations that transforms one matrix into the other. Okay, so it's important to note that row operations are reversible. So anything that you do as far as a row operation goes, you can undo that. If the augmented matrices of 2 linear systems are row equivalent, then the 2 systems have the same solution set. And then 2 fundamental questions about linear systems are the following. Question 1, is the system consistent? So that basically just means, does it have at least one solution? One solution or infinitely many solutions? If a solution exists, question 2, is it the only solution? So is the solution unique? Is it really one solution, or is it infinitely many solutions? So this brings us to existence and uniqueness. So existence and uniqueness of a system of linear equations. So here's an example. We want to determine if the following system is consistent. That's just another way of saying, does it have a solution? So here's our system in equation form. Here is our system as an augmented matrix. So all you do at the beginning is you take your system and you rewrite it with just the coefficients for your variables in your columns, and then your answer column to the far right. All right, so let's do a few row operations and get to our answer, our solution, if there is one. So let's go ahead and get our x1 in our first row to not be a 0. So just interchange the 2 rows. So my note that I write myself when I interchange 2 rows is I put it on the row that I changed pretty much. Well, if you're interchanging, you're technically changing both. But I would say something like this. Row 1 interchanged or replaced with row 2. That's the note I would write myself for what happened. Okay, now moving forward, let's eliminate the 5 down here. Let's get this to be a 0. So there are multiple ways to do this, but I'm going to go ahead and take negative 5 halves times row 1 and then add it to row 3. So my notation for that, I would just write it down here to the side. I would say negative 5 halves times row 1, and I added that to row 3. And the solution, the equation that I got as a result, is in row 3. That's why I write my note next to row 3. So let me just walk you through that really quick. So negative 5 halves times 2, let's write that off to the side, would be negative 5. Okay. Negative 5 halves times this negative 3, so that was this one, times negative 3 would be 15 halves. Okay, so 15 halves. And technically these have x's on them, so this is x1, this is x2, sorry for my writings, a little squiggly. And then negative 5 halves times 2, so that would become negative 5. Oops, not a minus, or not a plus, so minus 5, x3. And then don't forget your answer column. Negative 5 halves times 1 would be negative 5 halves. And so I'm just writing this so you can see what we did. So that's negative 5 halves times row 1, and we added that to row 3. So I'll put it underneath so you see it. Okay, so here's row 3. And so we had negative 5 halves times row 1 plus row 3. And so if we start adding, we have no x1s. Those got eliminated. That's why there's a 0 here. And then if you find the common denominator, this becomes negative 1/2 x2. That's where this came from. And then here we get 2 x3s. That's this right here. And then we end up getting this that it equals negative 3 halves. So that's where this new row 3 came from. So a lot of times it's hard to do these things in your head. So please, if you think you might get lost or just need to, I always write them out. So I write out my steps to the side, and then I write a note for what I did to get there. So now if we want to get a 0 in the x2 column of our last row, what we can do is negative 1/2 times row 2 and add that to row 3. So I have the work over here to the side. This is 1/2 times row 2. Here's row 2. So 1/2 times that is here. And then this was row 3 from our previous form of our matrix. So I just copied it here. And so if I add those, 1/2 times row 2 plus row 3, notice x2 gets eliminated, so that's 0, like we wanted. But then x3 also got eliminated, so that's 0 as well. Remember, we want 1s in the diagonal, so this is actually not something we want, but it happened. And then we end up getting this equals 5/2. Okay? And so now, technically, we would, well, usually we would keep going, but we're going to stop here because of what this is telling us. This augmented matrix is in triangular form because we have zeros down here in this triangle. And to interpret this, think about what it says as equations. The first equation says 2x1 minus 3x2 plus 2x3 equals 1. That's fine. Row 2 says 1x2 minus 4x3 equals 8. That's fine. But then row 3 says 0x1s plus 0x2s plus 0x3s, so no x's, equals 5/2. So this is a false statement. This doesn't make any sense mathematically. So remember what happens if we have a false statement, that's no solution. And so because this can never be true, then no values of x would ever make this happen, and they'll never satisfy our equations. And so this is an example where our system is inconsistent and it has no solution. Okay, so that is our introduction to matrices. And what you want to remember is to stay organized. Remember your 3 row operations that you're allowed to do to a matrix, and then what your goal is to solve for your variables. 1s in the diagonal and 0s elsewhere. All right, that's it for this one.